What specific problem does your proposed reward-aware compute-optimal test time scaling (TTS) method address within the domain of large language models, LLMs, and how does it differ from previous TTS approaches?
The proposed reward-aware compute-optimal test time scaling (TTS) method addresses the challenge of optimally allocating computational resources during inference to enhance the reasoning capabilities of large language models, LLMs. Unlike previous TTS approaches that typically utilized a single process reward model, PRM, for verification, which often led to out-of-distribution OOD issues and suboptimal answers, our method integrates reward information into the scaling strategy. This integration allows for a more nuanced adaptation of the compute allocation based on the specific policy model, prompt, and reward function, thereby improving the overall performance. Our empirical findings demonstrate that this reward-aware strategy can significantly enhance the reasoning performance of smaller models, enabling them to outperform larger models under the same computational constraints. This approach emphasizes the importance of considering rewards in the TTS process, which was previously overlooked in existing methods.
Can you elaborate on the step-by-step workings of your proposed compute-optimal TTS strategy, including how the MDP is structured and how rewards influence the decision-making process?
The proposed compute-optimal test time scaling TTS strategy is structured as a Markov decision process, MDP, defined by the tuple SAPR gamma. In this framework, S represents the state space, A is the action space, P is the transition function that defines how states change with actions, R is the reward function that evaluates the quality of actions taken, and gamma is the discount factor. The process begins with a prompt, X, sampled from the input space, X, where the policy model generates an initial action, A_1, based on the state, S_1 equals X. As the process continues, the policy receives rewards, RS_T, A_T, at each step, influencing the selection of subsequent actions and guiding the model towards optimal responses. The compute-optimal TTS strategy incorporates a reward-aware approach, where the reward function, R, is integrated into the decision-making process, ensuring that the model adapts its scaling strategy based on the specific prompt and the rewards received, ultimately leading to improved reasoning performance across various tasks.
Could you provide a detailed example illustrating how the best of N method works in your TTS framework, including how the selection process is executed after generating multiple responses?
In the best of N method within our test time scaling TTS framework, the policy model first generates N responses to a given prompt. After these responses are produced, a selection process is executed using scoring and voting methods to determine the final answer. Specifically, each generated response is evaluated based on its assigned scores, which can be derived from various scoring methods such as PRM-min, PRM-last, or PRM-avg. The final answer is then selected through a voting mechanism, where methods like majority vote or PRM-max aggregate the scores to identify the response with the highest score, or the most votes. This process ensures that the most promising response is chosen based on the collective evaluation of the generated outputs, enhancing the overall reasoning performance of the model.
What empirical advantages does your reward-aware compute-optimal TTS strategy offer over traditional methods like majority voting or other existing TTS strategies, particularly regarding model efficiency and performance?
The reward-aware compute-optimal TTS strategy demonstrates significant empirical advantages over traditional methods like majority voting and other existing TTS strategies. Specifically, it can be up to 256 times more efficient than majority voting, while improving reasoning performance by 154.6%. This strategy allows smaller models, such as LLM-A3, 2-3B instruct, to outperform much larger models like LLM-A3, 1-405B instruct, by effectively allocating compute resources tailored to specific prompts and problem difficulties. Additionally, the integration of reward functions into the TTS process enhances the selection and evaluation of responses, leading to more accurate outputs compared to methods that do not consider rewards. Overall, the reward-aware compute-optimal TTS strategy not only boosts performance, but also optimizes resource usage, making it a more effective approach for enhancing LLM reasoning capabilities.
How did you validate the performance of your TTS method in the experiments, and which metrics or datasets were used to ensure the robustness of your results?
To validate the performance of our test-time scaling TTS method, we conducted extensive experiments on competition-level mathematical datasets, specifically the -500 dataset, which contains 500 representative problems. We employed various policy models from the Llama 3 and 5 families, utilizing the instruct version for all models. The evaluation metrics included pass-at-1 accuracy, which allowed us to categorize problems into 3 difficulty levels: easy, medium, and hard, based on absolute thresholds of accuracy. Additionally, we compared the performance of our TTS method against other strategies, such as majority voting and long COT-based methods, to demonstrate its effectiveness. Our results showed that compute-optimal TTS significantly improved reasoning performance, achieving up to 256 times more efficiency than majority voting, thereby ensuring the robustness of our findings.
From your findings, what are the key limitations of your approach, particularly in terms of PRM generalization across different policy models? And how might these limitations influence the application of TTS in various scenarios?
The key limitations of our approach primarily revolve around the generalization of process reward models, PRMs, across different policy models and tasks. Our findings indicate that PRMs struggle to generalize effectively, particularly in complex tasks, which can lead to suboptimal answers when using out-of-distribution OOD PRMs. This limitation is exacerbated by the fact that the choice of optimal test-time scaling TTS strategy is highly dependent on the specific PRM employed, as evidenced by the varying performance of different PRMs with the same policy model. Additionally, the performance of TTS is sensitive to the characteristics of the training data used for PRMs, which can bias the output length and affect the overall reasoning capabilities. Consequently, these limitations may hinder the application of TTS in diverse scenarios, as the effectiveness of TTS strategies could be compromised when faced with varying policy models and problem complexities.